Hello, Chem 20s. This is Mr. Kemp. Our first lesson we're going to do together is going to be on intermolecular forces, polar versus nonpolar. If we take a look at this slideshow, I would assume that most of you have copied the notes already because that was what I asked you to do. So we're going to look at comparing the two. We're going to start with polar, then we're going to go and spend the last two slides looking at nonpolar. Since molecules are made up of charged particles, we can say that a polar molecule is one in which the negative electrons are not distributed equally or symmetrically between two atoms of a molecule. So if we were to think about this, right, the outer electrons are all going outside. So let's grab a model here. We have HCl. We know that there's electrons flowing around the chlorine and that there's also negative electrons flowing around the hydrogen. For us to have a polar molecule, this sharing means that these electrons that are being shared are not going to be shared evenly. Now, when we look at a model kit, it looks like every bond is shared evenly because the bonds are all the exact same. This is not truly what happens. So for polar to occur, one, the sharing's not going to be even, and then two, what it says is that it's going to also have an asymmetrical geometry. Now, the only way we can talk about an asymmetrical geometry is if we know what symmetry means. So I want to do a quick review. On this, we have, of course, a happy face and a Christmas tree. Both of these would be considered symmetrical because, again, it's a mirror image of each other left to right, where asymmetrical would be my coffee mug or would be this smiley emoji with the tongue sticking out, meaning it's not the same left to right. There's no symmetry in this picture. Well, that's what we're going for when we talk about polar molecules. We want asymmetry, not the same side to side. Now, if we take a look at this, the only way that we can talk about polar or nonpolar is if we look at electronegativity values. Now, if you grab your periodic table and you were to look on your periodic table, you would see that there's a number on every element that we have not talked about yet. Those are called electronegativity values. Now, a quick scan of your periodic table would show you that everybody has an electronegativity value except noble gases. Well, there's a reason for this. If we look at the definition of electronegativity, the ability of an atom to attract shared electrons, well, that more or less explains it. A noble gas doesn't want to share electrons. Therefore, a noble gas isn't going to attract electrons. A noble gas, those, remember, are the kings and queens of our periodic table. They're already perfect. They don't want to gain electrons. They don't want to lose electrons. They're going to have no attraction whatsoever for these electrons. So if we look at the table, a quick scan will show you that. Down here, bottom left corner, francium has the smallest electronegativity value at 0.7, and it gets larger as we go up. Hydrogen is 2.2. But along with the numbers getting larger when we go up the table, they also get larger as we go from left to right. And so you'll notice that fluorine has the largest electronegativity value at 4.0. It has the most ability to attract electrons. It's going to pull harder than anything else on that table. It wants those electrons. It wants that negative charge. Now, the example we started with was HCl. And hydrogen chloride, hydrochloric acid, whatever you would like to call it. Now, what I would like us to do is, we know these have to be shared because this is molecular, right? Two nonmetals. So what I want to do is I want us to look up the electronegativity values. What numbers do these guys have? And so if we check our table, we will see that hydrogen has a value of 2.2. Chlorine has a value of 3.2. That means Chlorine is pulling harder, getting more of that bond. So instead of that bond being shared evenly, it's not. It looks more like an egg. Chlorine is pulling harder. Think of it like a game of tug of war. I'm on one end, I'm chlorine, I'm pulling with a force of 3.2. My twin is on the other hand. Cameron is pulling with a force of 2.2. I'm pulling stronger than him. I'm going to get more rope. I'm going to have more of the bond. So what you happen to see is it's going to take on this shape like an egg. Although it's shared, I'm going to get more of that bond on the chlorine side. Cameron's going to get less of the bond on the hydrogen side, which means because it's a higher electronegativity value, and I've got to escape this here for a second and go back to a pointer. So what we're going to see is hydrogen is going to be slightly more positive. Chlorine is going to be slightly more negative. Now this is just slightly, and those weird symbols that you see, those are deltas, delta positive, delta negative. The chlorine is going to take on a slightly more negative side because it's got a higher affinity for the electronegativity values. So we always draw an arrow pointing to the side that is the bigger number. The arrow points to the negative one. And so we have an electronegativity pointing over here to the chlorine. It pulls harder, bigger number. So let's read through the slide. A polar covalent bond is a shared bond in which the electron density is more localized on one end of the bond. One end is slightly positive, that's our hydrogen side, and one end is slightly negative, that's our chlorine side. So there has to be this discrepancy amongst electronegativity values. The electrons are more likely to be found closer to the nucleus that exerts a greater pull. I pull harder, those shared electrons are going to be slightly closer to the chlorine side. This unequal charge distribution within a polar covalent bond gives what we call a bond moment, this bond dipole. That's what this is. We're always going to draw an arrow pointing to the most electronegative side, and we're going to put this little goofy line here so we can see this is the positive side, this is the negative side. They are going to share unequally. Now, second point, when I tried to compare items, so both of these are the same shape, they're both linear, one's hydrogen fluoride, one's hydrogen chloride, I picked two halogens. Well, when we look up their values, we will see that hydrogen is still, oh, I need a pen here. Hydrogen is still 2.2 on both of these. However, fluorine is 4.0 on this one, and chlorine is 3.2 on this one. So we already know, although, and I need my little pointer tool back, although the first example, hydrogen fluoride, we're going to point towards the fluorine. And although in the second example, we're going to point towards the chlorine, and chlorine is more electronegative than the hydrogen, and the fluorine is more electronegative than the hydrogen, both of these are polar. But we can say because the difference is greater between hydrogen and fluorine, there's a bigger difference when I subtract 2.2 from 4 than when I subtract 2.2 from 3.2. We're going to say that the hydrogen fluoride, it has more polarity. It's more polar than HCl. It pulls harder. There's a bigger difference here. Because if we take a look, the difference here is going to be 1.8, and the difference here is going to be 1.0. HF wins. And we'll go back to our pointer here. Okay, let's look at the example of carbon dioxide. I want you to take a second and I want you to pause this and draw carbon dioxide for me, please. Now, I think we all know what carbon dioxide looks like. So we have carbon, and if you haven't paused it, pause now before I give you the answer. Now, We can quickly look up these values. So carbon is still 2.6. Oxygen is still 3.4. And what you want to do is ask yourself, who is going to pull harder? Oh, I'm frozen here. Here we go. So it looks to me like carbon is slightly more positive. Oxygen is slightly more negative, bigger electronegativity value. So in this case, between this bond of carbon, oxygen, this double bond, oxygen is going to pull harder than carbon. In this other bond, I'm going to flip it because oxygen is going to pull harder to the left than the carbon. So we have one oxygen pulling harder than the carbon twice. One's pulling directly left, one's pulling directly right. So it says at the top, however, just because you have a polar bond does not mean you are polar. There are polar bonds in here. But what I want you to notice is they are going to cancel each other out because one is going left, one is going right, and the difference between them are equal. So they're going to cancel each other out. Now, an easy way to think of this is, let's pretend we're having a tug of war. I pull with a force and you pull in the opposite direction with the same force. Nobody's going to win. When we add these bond dipoles together, one goes left, one goes right, nobody wins. Therefore, this, when we are all done, is not considered polar when you add them together because there is not a geometric asymmetry. It's geometrically symmetrical, and that doesn't work for us. There's two criteria. So here's carbon dioxide. Again, it's not showing the double bond. It's already bonded there for you. I just want you to see left and right in this case.